Hello, hello, hello. Sorry, hello. Oh, we're coming. We're all coming, including the board. Hang on. Here we go. Okay. Oh, good afternoon. All right. I see. Good afternoon. Okay. Hang on. Just. Oh, excellent. Good afternoon, Samira. Good afternoon, Samantha. I'm assuming you can hear me. Well, we'll know in a second. I think you can hear me. Good afternoon, Key. Good afternoon, Valentina. Good afternoon, Christina. Good afternoon, Bree. Good afternoon, Juliana. Good
Good
morning.
afternoon.
Thank you. Oh, was that Michaela? Thank you. Awesome. Just made my day. Thank you. And Avatar. That's like a triple. That's a hat trick. Okay. Wait. I think it was Michaela. And I think I'm pronouncing that right. But let me know. And there's closed captioning, so you can definitely know if I pronounced it right. Oh wait, where was I? Bree, good afternoon. Juliana, good afternoon. Oh, that's where it was because James said good morning for reasons. Good afternoon, Mario. Good afternoon, Toiba. Good afternoon, Christopher. Okay, and there's more. I also know this. And extra special hello to Michaela, Juliana, Bradley, Toiba, Key, Bree, Mario, and Christopher for having avatars. And hang on, we're still, the board is coming in. Oh, and there's more in the chat. Oh, yeah, there's this weird thing too. Oh, hang on. I realize now there's like a whole chat thing that goes on that's, hang on. I forgot to warn us all that, okay, wait, did I say hello to Juliana? I did. Okay, right, because there's always this weird thing that it is accidentally sometimes possible for someone to accidentally send a chat to my board rather than to me, even though my board is me, but I don't see the chats on the board. Okay, but I don't think that's what happened. All right, anyway, why am I now? I'm in two places at once. Hold on. Okay. Now the participant thing is locked again. Okay. So here we are. So it's good to see you all. I think we're, oh, and there's more people coming. Okay. Announcements and then we get rolling. So I've missed you. It's been a long week. I mean, so I think it's been a longer weekend for you than for me. I don't know if it's been a pleasant weekend. But anyway, welcome back. We're going to do physics, I think, for good afternoon, Dante. Thank you. Awesome. Wait, does that avatar mean he's a fireman? No, wait a second. That's not, is that, all right, anyway. Sorry, okay. All right, wait, so announcements first. We're all doing well. We're all catching up with each other. I do see, I've turned back a lot of things that, well, where should I start? Okay, so first of all, thank you for your exams. Congratulations on being done. I know that was no joke, to put it mildly. Well, I don't think it was a joke. I know you probably didn't have a pleasant weekend. I know, in fact, let me get to this. I certainly, so I have most of, I think I have all of them. Sorry. More people coming in. Hang on. Okay. Yeah. I can say, I always like to make this explicit if I can. I'm looking at everybody who's here. I'm looking at all the exams right now as I say this. So certainly I can say this. Everybody who is in the room right now, not only people who are in the room, but certainly everybody who's in the room right now, okay, I'm going to triple check this, make sure I don't say the wrong thing. Yes. Everybody who's in the room right now, and actually there do seem to be a lot of people missing, which is not great, but okay, everybody who's in the room now, I have your exam. I mean, like I got it from you. And I believe I can even say, for everybody's in the room now, that everybody in the room handed in the exam when they were expected to hand it in, or if in some occasional cases there was a private arrangement made because of a personal issue, then the exam came in time for that arrangement. In other words, all of you, I'm going to check one more time because actually I don't say this lightly. I don't want to say this lightly. And also I have not graded them yet because I just got them late last night. So I can't tell you how well you did on them yet. And so I'm not going to dwell all. I'm not going to dwell all class about this. Well, okay. The simple thing I could say is for the most part, if you're in the room right now, you have turned in your exam. Let's start with that. So that's an achievement. I don't think it was a joke. I think for some of you, it might have snuck up on you and seemed a little bit more challenging than you might have expected or something, given that you were allowed to use resources and stuff like that. I would hope and expect that it's a load off all of your minds that it is turned in now. And again, let me just say, anybody who's in the room right now, you turned it in. So that's already an achievement, really. And it's something you should already feel relieved and proud about. I do not have numbers yet. I don't know how quickly I'm going to get you numbers. It will not be as quickly as I like or as you like, but I will get them to you, and feedback and stuff. But of course, I will get them back to you. It will not be tomorrow. I don't think it's not going to be that fast. But they are looking good so far. We will talk about them, and everybody who's in the room right now is still like very much in the center of this course and trucking along, which is good. Whatever your experience was taking that exam. Oh, okay. Thank you for the private chat, actually. Okay. There's a private chat that's actually kind of helpful to me right now because yes. Okay. So to be, the reason I'm stumbling around here a little bit is it is actually true that a couple of the exams did come in slightly. A couple of exams did come in late without sort of a warning or arrangement. Not many, and I'm not saying that to shame or anything like that, but okay, to be clear to everybody in the room, if your exam came in late without any prior arrangement or prior warning or notice, okay, because it's an exam and because it's so loose in so many other respects, such as the fact that it's take home and you can use resources and blah, blah, blah. Because of that, I am sort of rigid. I have to be rigid about the timing. So just to be clear, everybody, for those people whose exam did come in a few hours late or something like that, or like a half day late or something like that, on the one hand, that does not mean I'm not going to read it. It does not mean I'm not accepting it. It does not mean the person automatically fails or doesn't get a grade. No, nothing like that. Like if you did an exam, you did an exam, and I'm going to read it and I'm going to mark it and you're going to get credit for it. It is true, just to be clear and consistent, and so that you know for the final, and I think I said this before, but so that you know for the final exam, and also honestly, so that everybody in the room who did kill themselves to get this thing in like exactly by the deadline. Yes, I do want to say that if anybody's exam did come in late without any prior warning or any kind of prior like arrangement, what does have to happen is I do have to take off some points for that. That's the bottom line. I'm not going to fail them. I am going to read their exam. I'm totally going to take it. And I'm not going to grade the exam with like a bias. I'm not, you know what I mean? I mean, I'm whatever quality of work they did in the exam, they're going to get total like merit for the quality of that work. But there will be a point penalty for an exam that came in late. And just to be totally clear, the reason I'm not saying what that point penalty is yet is it is sort of, it is sort of related. No, it's not sort of, it is entirely related to how late it is. Assuming no arrangement or prior notice or notification was given, the better people communicate with me, the better things go in general. And I guess I'm saying this right now also for the sake of the final exam and all of that. I will say right now, to be 100% clear, and all this is partly to reward the efforts of people who really like made maybe some contortions and sacrifices to meet the deadline, and so that they know that I know that, and that other people aren't getting an advantage that they could have had if they had known. What I'll say, to be super explicit and not to call anybody out, I happen to know that one exam came in literally 1 minute after the deadline. Literally 1 minute, as I tried to explain to that person, is literally the smallest possible amount of lateness that could even be registered on a computer, right? Like if it was 45 seconds, then if it was 20 seconds, the computer wouldn't even say it or whatever. Or put another way, it might have been 20 seconds, and therefore the computer rounded up and said a minute. So a minute, like it could not have been any less late than a minute, right? So I'm laying this out just so that everybody knows where my headspace is on this kind of thing. There's a huge part of me that says, well, like somewhere there has to be a deadline, there has to be a cutoff somewhere. People are killing themselves to respect it. So somewhere there has to be a cutoff, and it has to be clear, blah, blah, blah. That's the point of a deadline. There's, of course, another part of me that says, okay, but if a person's 1 minute, first of all, that might have been a minute difference between their clock and my clock. Like, really? Am I going to treat a person who's 1 minute late? Am I going to treat them the same way that I'm going to treat a person who, like without any warning or whatever, like went all the way into the next morning or something, and took the whole night to work on the exam when everybody else did it? No, I can't. That's not right either. That's like weirdly arbitrary. So just to be clear to everybody, I'm going to move on this in a second, but just because there are a couple of things in the direct chat of concern already on this. Person who's handed in 1 minute late is going to lose literally 1 point for that. Just to make the point that, okay, like we have to like have a cutoff somewhere, blah, blah, blah. So they're going to literally lose 1 point, which I'm hoping, as much as that person, I'm literally hoping and rooting as much as that person, that 1 point is not going to end up making any real difference in their ultimate performance, like other than symbolic, right? But then the flip side of that is like, yeah, if the exam came in hours, there was no discussion or no communication or no like you didn't give me a heads up before, that's a different thing. And so there will be some kind of point penalty, not enough so that you're like now sunk in the water for the whole course, but enough so that it makes a difference. And like the next time we communicate with each other, okay, I think I will look in the chat, and there's also people in the waiting room. But the real lesson for this whole thing, especially even with the final exam, oh yes, actually, and I will look in the chat. I can't say much more concrete, and I don't want to spend the whole period on it because like I don't have them back yet, obviously. So there's not as much to talk about. But I will say this to everybody before I look in the chat. Whatever experience you had taking that exam, like whatever you thought it was exactly as you expected, or it was surprising, or when you found out like, ooh, I should have given myself more time for a thing like that, or whatever. I am telling you the final exam is a very similar experience. Very similar. I mean, it's a little bit more compressed in time because we run out of time at the end of but it's the same format, the same arrangement, the same deal. So psychologically prepare yourself that way. And do know there are people in the room that realized something before the exam was due, like maybe even before it was posted or a couple days before it was due, that realized something, like they had a conflict with another class, and they communicated with me. And then depending on what the situation was, some certain amount of concession or not was able to be made. But it's very much about communication and anticipation. That's the key. Don't like at the last minute decide that you really needed 2 more days. Okay, whatever. But I think, again, if you're in the room right now, then I have your exam and you did your exam. And even if at worst, it was a little bit later than it should have been, and even if at worst, I'm taking off some points to make a point about that. If you're sitting in the room right now, then you have turned into me a thorough, complete, and honorable exam, is my impression so far. And so you should be feeling like you are still quite centrally in it to win it with this course, and like you're on top of things. And I still might owe you an old homework or two, depending on who you are. Okay, I'm going to look in the chat. I didn't mean to get that bogged down on that. Hold on, look in the chat. Okay, hold on. Wait, hold on. I'm looking through the direct chat. One second. Okay. Hold on. I'm just responding to direct chat. Okay. Okay, wait, so things are happy. Sorry, there's one more thing in that. Okay, there's actually, I don't mean to do all this right now, but there's like a couple of things in the direct chat, because yeah, I mean, so look, again, if you're in this room, the exam came in, and that's like the huge, most important thing. Like we did, one of the great things about science is this whole concept of significant figures. I know everybody hates it. I know everybody thinks that's like the worst thing in science. But if you think about it metaphorically, like I'm on the first significant digit right now. The first significant digit is like, did you even do the exam or not? Because some people don't, right? That's a first, like, or and you guys did. Okay. It was like kind of not a small deal to do that exam. You did now, and that's a big, so already you're not the problem, and you're not going to have a big problem in this course, right? Really. Then there's the second significant digit, like a whole nother scale of like, now we can get to like more detail and refinement, move from good versus bad to like excellent and amazing versus competent or whatever. On the second level, there's the issue of like, okay, getting in and on time. Partly, again, I'm addressing all this because I want it to be clear for the final. Also, I know that I send very mixed signals on all this stuff. With homework, it's a complete loose, it is a loose deal with homework, and I want it to be. But with exams, I want it to be a tight deal. That can be confusing. I'm very aware of that. That is also why when I say that for the couple of exams that did come in late or whatever, that there will be a penalty, there will be a recognition of that, a point penalty, because we do have to be consistent with all students and all that stuff. It's not going to be so much as to break you or to damage you. Like, there's no one in this room that, as far as I know right now, I'm going to put it this way and I'm going to move on. As far as I know right now, with the information I have right now, and again, that's having not yet graded these exams, there's no one in this room now that's written them out, that's written themselves out of an A. If you see what I'm saying, it doesn't mean everybody's getting an A, but I don't know. They're certainly not from like lateness on the exam or something. No one's like written themselves away from an A yet. Now I still have to grade them, of course, but I do just want to make it clear before the final exam that yes, like, because there's so many other things that are loose associated with the exam, you do want to be tight on time, or more than that, on communication. Now that you know how long these things take, or how that they do take more than they seem like they would, since they're open book and all of that, now know that for the final exam. And if you anticipate a problem, or if you start to anticipate the possibility of a problem, reach out to me and we'll discuss it. Even if you end up changing your mind, you don't need the extra support. Okay. So, okay. But that's all. Okay. Now on a completely different, I mean, and all of you, again, please, what the email and my phone number are for, for texting, I'm going to put it right now in the chat one more time, just in case. Like there's always, okay. There's a lot going on in the direct chat. Yeah. Yeah, there's a lot going on in the direct chat. Hold on a second. Hold on. So. Okay. Okay. And also I want to make it clear there's more than one thing happening in the direct chat. So if you are one of the people in the direct chat, it's not just you, and it's all good. Okay. And if I sound weird right now, I always sound weird around exams in a way, because they, it does tend to, whatever. But There was one other thing. Okay, there was something else I was going to say about it, but I don't remember. Oh, I was going to put my phone. Oh, let me put again, just in case. I think it's pretty clear to most people, but in the chat, just in case. Now they've, you know what also it is? You all know this. I don't know if you know it you all know what I'm about to say. You just may not know it consciously. You know, there's always like the class, and the class goes a certain way, and then there's the first exam, and then the class like becomes like reality of a different kind. Like something always like changes in a way in the whole psychology of the whole group. Like once there's an exam, and then once there's grades back from that exam, like it always, and I hate that. I mean, it doesn't always make things worse, but it just sort of, everything's kind of dreamlike until everybody gets their first grades back. And then usually office hour times increase and stuff like that. So, or then suddenly people start reading the syllabus and actually knowing what, I don't know. So just in case, what I'm saying is, and that's all as it, I mean, it's neither good nor bad, but it's like kind of weird. So just in case, what I'm doing now, even though I think many of you have been very, very clear on this and very happy to take advantage, I'm putting my email address, the preferred one, back in the chat. I'm putting my phone number for texting back in the chat, just so now we know, like, if you need anything, it's just better to tell me in advance or ask me in advance or whatnot, blah, 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 blah. Okay. It's another way of saying right now, even though I sound like a way that I don't want to sound, this is all another way of me saying one thing about the first exam. It always shakes people up a little bit, but the real message I want to send right now, whether I know, even though I don't know your grades, or maybe because I don't know your grades, one real thing I want to say right now, if this experience like straightened us all in our seat or something somehow, is it's not too late for anything at this point. Nothing is too late for anything if suddenly the exam sent out like a reality flare to some people or whatever, fine, but don't, no matter what happened on that exam, no matter who you are, no matter, assuming you did it, no matter what you did on that exam, I can say with pretty great confidence, you did not write your ticket to doom. You didn't. You maybe figured out that we need to do something now before the final. So there's my phone number again, and there's my email. So let's do it, whatever it is. But it is not too late for anything for anybody at this point. I mean, I guess that's my real message, whatever that means. Okay, and no problem. Thank you, direct chat people. Oh, I don't even know how people got in. I didn't even see the waiting room. Sorry. But okay. So we have to get back to physics now. The other thing, we have to get back to physics. But the next 2 days are again going to be sort of, you could see there's some sort of chaos going on in my side of things. The next 2 days are going to be logistically weird again, kind of like last Wednesday was. They're going to be weird in the sense that there's going to be some choppy combination of synchronous and asynchronous. Again, like there will be some combination of me posting a video that I make for you that I ask you to watch and some amount of real in-time class interaction. I wish I could tell you exactly how that's breaking down right now. I can't. I apologize, but just be in advance. Look out for that communication that will come tomorrow, just like last time, that will say you get 7 points or you get some number of points just for reading this communication and affirming that you got it. Okay, and that's no joke. Because I think it's hard for everybody. You'll get points in the morning for getting some kind of communication that says there'll be some kind of abbreviation of class or some kind of video. And obviously any video I post instead of class will make up for the time. And the bad news is it's not participatory in the same way, but the good news is you can like watch it at whatever hour you want. Okay, so it's something like that. In fact, now I'm going to go on, but that's going to happen. It's not going to happen for the rest of the course for every week, but it is going to happen again in some way over the next 2 days, Tuesday and Wednesday. So can I just get a show of electronic hands if you just heard me say that you have to look out for communication tomorrow morning? Great. Thank you. Awesome. Okay, great. That is good enough for me. Okay. And anybody who, and great. Oh, he's clapping. Oh my God. Okay. Zoom every time great. Okay. So that's good enough for me. So thank you for understanding. So I will send out that communication and great. Thank you, Samir. Awesome. Oh, sorry. Thank you, people. Thank you. And with that point thing, that whole deal with that is, right, like I send you a communication, then you just confirm by writing yes, which you all were very good about doing, and then you get the points back from me. The minute you get the points, you know that I know that you get the point. All right, so now let's do some physics. We're gonna pick up right from. Ooh, that's an X. Wait, does X mean no? Wait, you can put your hands down now if they were up. But if you're putting an X up on purpose to say that there's a problem, definitely let me know in the direct chat. But I think you can all put down whatever signals. Hold on. All right, one last thing. Okay. Cool. Okay. All right. Oh, okay. Okay. Great. Great. Okay. Oh, okay. Fair enough. Neither do I. Okay. 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 I promise I'm trying to teach. I'm gonna look at one thing and then we're gonna recognize it. Okay, I do not know how to. Okay. Well, okay, I'm gonna say. I mean, I think we can. There is one reaction that's up that I guess we don't know how to take down, and it's no shame, but it is kind of funny that we don't know how to take that down. Okay, I guess if anybody wants to private chat and help anybody take down their electronic reaction, it might be helpful. Or if I could know, that would be great. Why am I getting? Okay, I'm just gonna go. Thank you. All right, that totally counted as multiplayer co-op. Like that was a double because it even made a set. Thank you. Okay. I don't or whatever just happened. Thank you. Okay. Apparently I'm very distracted. Here we go. Okay, we're going to start right here. This is the first equation written on the first page of today's notes. This equation is like where we left off right before the exam. I'm going to quickly back up slightly and like review it slightly. I'm not going to go through the whole problem 4 thing again. I'm going to see what your responses were, but I'm going to remind you sort of what it means, right? What it means. Okay, just to remind you, that equation right there, y equals a cosine omega t plus or minus k of x. Well, it's assuming that y is this axis and x is this axis, and ultimately it could be any two axes. It could ultimately could even be two things happening on the same axis. But what we're saying is we have a bunch of vertical oscillators, all distributed uniformly, all set up equal distant from one another along a horizontal axis, right? So you've got a vertical mass on a spring next to a vertical mass on a spring next to a vertical mass on a spring, all distributed at equally spaced intervals along a horizontal axis, right? Each one of them is identical in the sense that each one of them has the same omega and the same A. Each one of them has the same omega, the same angular frequency, which in turn, if these are all masses on springs, for example, then it means each one of them is the same mass magnitude and the same spring stiffness, right? The same M and the same K. So you've got all these same springs all distributed equally along a horizontal axis. But the catch is that each one has a phase, a phase constant. Sorry. Oh, yeah. Oh, yes. I'm sorry. Thank you, direct type person. Yes. It said, I'll read the handwriting out loud. Yes. It says a collection of identical vertical oscillators distributed uniformly along a horizontal axis. So uniform means constantly, means samely. So specifically in this case, it means equidistant along the horizontal axis, a uniform amount of space between each pair of oscillators. So yes, person who's asking about my handwriting, thank you. Yes, it says a collection of identical vertical oscillators distributed uniformly along a horizontal axis, and here's really the key point, and staggered in phase by a constant step. I mean, that's what it says. And what does that mean? Again, I'm at the risk of me getting all in the rabbit hole. Okay, I guess I will. Hold on a second. Oh, yeah. Oh, okay. Can I please go back from yeah, sorry. All right, let me go back for a second. Yeah, okay. So here's okay. Great. Thank you. And that totally counts as take a step back. So yeah, so what I'm saying, and again, what I'm talking about right now is kind of review from where we were right before the exam, but I'm reviewing so that we can, remind ourselves and move on. So what I'm saying here is this. Right. Remember, going back to whatever problem that was on homework 2, I can't remember. It was problem G or something, problem 1G or 1F of homework 2, remember that phi, the phase constant, is a constant, right? Phi is a number, phi, that little Greek letter that was added into the parentheses. Phi is a constant number of radians, and we call it the phase constant. What it represents is how far into the phase, how far into the cycle the mass already was, or the oscillator already was, at the moment that we started paying attention, that we started our stopwatch at t equals 0, right? I'm reminding you this, but let's get this straight so that we understand how this is functioning when it's not a constant and when it's multiple oscillators. The point of phi, when we originally introduced it, is that's the head start or the delay. It's called the phase constant, and what we mean by the phase constant or the phase is the head start or the delay of how many radians into the cycle we already were at t equals 0. So again, remember, if phi is 0, if you take the simple cosine expression that we used to be dealing with, where there was no phi at all, it wasn't that there was no phi at all, it was that phi equaled 0 in the first easy case, in simpler cases that we were doing. So when phi equals 0, the point is that the minute we started our stopwatch, the object was at what we would call the beginning of the cycle, i.e. all the way at the positive amplitude position. It was already displaced as far as it could be and as far as it ever would be from equilibrium. Like in the case of homework 1, there was no phi at all. We were ultimately just saying x equals a cosine omega t, because what we were assuming is we started our stopwatch when the mass was already way out at 15 centimeters from equilibrium, right? But if phi is some number, whenever phi is a number, I'll just remind you again, example, if phi is something like pi over 2 radians, right? Pi over 2 radians means 1/4 of a cycle, right? Because there are always 2 pi radians in one cycle, by definition. Right? So if phi equaled pi over 2 radians, then in this case, we're dealing with a vertical oscillator. Then we're saying something like this, right? If phi is pi over 2, then our equation for one oscillator would be y equals a cosine parentheses omega t plus pi over 2. What would that mean? Then, if you think about it, then at t equals 0, y equals a of times cosine of 0 plus pi over 2. So y equals, the most important parts always end up at the bottom of the page. Believe me, it's as frustrating to me as it is to you. No, it's probably more frustrating to you, but it's pretty frustrating to me. Anyway, when y equals a cosine of 0 plus pi over 2, I'm just plugging in now, like just to make it clear, then y equals a cosine of pi over 2. And what is cosine? Actually, I'm going to stop and ask since we have a little time. What in the chat? That was fast, but actually too fast. Oh no, it wasn't. It wasn't too fast. Sorry. That was fast. My bad. Okay, someone deduct points from me for being late on the intelligent. Yes, no, totally right. And even if you're already seeing things in the chat, I don't care. You could still put things in the chat right now or the private chat and confirm to yourself and to me that you're following what's going on. I do agree with them. I agree with Christopher and Michaela and Samantha that the cosine of pi over 2, I'm almost concerned that only 3 people are weighing in on this, but yeah, thank you, Valentina. Thank you. Awesome. And Juliana, thank you very much. Juliana, thank you. Yes, the cos and direct chat person, thank you. 2 of you, awesome. And Keith, and I love that you can do that. Okay, now we're talking. See, it feels like a class again now. See, everybody's happy. Thank you, Keith. Thank you, Bree. And thank you to direct chat people. Yeah. So cosine of pi over 2 is 0. Therefore, therefore, when t equals 0, y equals 0. Now, please notice, like as opposed to, I know this page is getting wackadoo, and I just want to make this clear. As opposed to, and I'll flip the page in a second, but as opposed to, if phi equals 0, then at t equals 0, y equals a. If you work it out, right? Like if there's no phi, if there's no phase constant, then the assumption, not the assumption, the math says, if you plug in 0 for t, the cosine of 0 is 1, 1 times a is a, right? So the whole point is, when there was no phase constant at t equals 0, the object was all the way at the edge, at the positive amplitude position. But if there is a phase constant, the phase constant is telling you how much of a head start or delay the thing had by the time we started the stopwatch. So the most clear example is the one we just did. Like if you say that there's a phase constant of pi over 2 radians, that sounds obscure, but you're basically just saying the thing already was a quarter cycle into its pattern when we started our stopwatch, meaning it was already back at the equilibrium position when we started our stopwatch. If it was pi rather than pi over 2, that would mean it was all the way at the other side at negative a when we start our stopwatch. Okay, etc. So that number, and I know we've said this before, that number represents a head start or delay in terms of the cycle measured in radians, and it's just a number. It's called a constant when it's just one oscillator, right? But the whole thing that you described to me in problem 4 of the exam, the whole thing that we're saying now, that's kind of deep, is that if we set up a whole bunch of oscillators and we set them up all next to each other so that they're all the same oscillators, except that the very 0th one has a phase constant of 0. So the very 0th one, when we start our stopwatch, is at the amplitude position. But the one very next to it is not at the amplitude position. It's like somewhere else, like the equilibrium position, say a pi over 2 ahead of the 0th one. And if the very next one, the second one, is pi over 2 ahead of the first one, which means that it's 2 pi's over 2 ahead of the 0th one, et cetera, if we set up all of these oscillators so that they're all, so that each one of them, we know exactly where it is starting in the cycle based on how far out it is along the x-axis, right? If we do that, if we have, you know, this situation that we've been talking, this situation, then now what we're saying is that for any one oscillator, its individual phase constant phi is equal to kx, i.e., what we're saying each one has its own phase constant, but each one is at a different x. So each phase constant is different from the next one. So the phase constants are constants for each individual oscillator, but it's not a constant across the board. It's not constant anymore, the phase from one oscillator to the next. What's constant is the amount by which these phases are being stepped, increased or decreased, right? What we're really saying now I'm starting to expand this a little bit more than we did 2 days ago. What we're really saying in this case is if we were to make a graph of phase shift for any given one of these oscillators, like, wait, let me back up for a second more. What we're really saying is, like, if you name the oscillator, I could name the phase shift, right? If you say, okay, I want to know the 5th oscillator, i.e. the oscillator that's at the position x equals 5, what's its phase shift? Like, is it 0? Is it like pi over 3? Is it like 3 pi's over 3? I would say, well, it's 5 pi's over 3. If you're talking about the 5th oscillator, if you're talking about the oscillator at position x equals 5, then its phase constant, its phase delay, or its phase head start would be 5 pi's over 3, or 5 pi's over 2, or 5 pi's over 4. It would be 5 times whatever the step in radians per meter actually is. And what do I mean by that step? I'm saying, oh yes, if you think about it, and you may or may not have thought about it this way before, if you think about it, if you were to draw a function, a graph. Now, this graph, just so you know, if you've been sort of phasing out because you understand everything I just said, because you feel like you just wrote it all up for problem 4, that's great. It's awesome. Now, this graph I've never made before. You may or may not, it may or not have occurred to you, but this is like slightly new. I'm saying, like, if you make a graph of radians per meter, right? Such that, you know, for for the oscillator at the 0th meter position, at the edge of the meter stick, its phase shift would be 0, right? But as you notice, the phase shift is directly proportional to the advancement of x, i.e., if you made this graph, the rise in phase shift over the run in x, right? That slope of that graph, is constant, right? It's a constant number. It's measured in radians per meter. And that slope of that graph, the rate at which phase constant for any individual oscillator increases or decreases per increase or decrease of horizontal spacing, that number is called K, right? That's what we mean by the angular wave number. Oh, great. I just saw in the chat. So K, so someone just wrote in the chat, so K is the slope? Yes, exactly. K is the slope of that graph. Yes. K, the angular wave number, is the slope of that graph. Exactly. And let me be clear to everybody again. By K, I mean the K that came out of your lab 3, the number that you were using in lab 3 that you probably did not feel very comfortable with during lab 3. I mean, certainly I didn't when I first did lab 3. I mean that number, just to be clear again, I don't mean the K of spring stiffness. These are two, so that's why I write it. You could write it any way you want as long as you're straight in your notes. It does not mean the same thing. Like it's not the same thing as spring stiffness. Spring stiffness is measured in newtons per meter. This thing that someone in the direct chat is correctly identifying, this thing is number of radians per meter. This thing, angular wave number, K, right? I mean, so this is the K in when we say this. Okay, when we say this, okay, I'm going to write it one last time. Like Kx is phi. I just want to make that clear to everybody. Like phi, like if you just wrote it as phi, this would be the equation of one particular oscillator. But we're capturing this whole collection of oscillators by expressing phi as a function of a variable called space. Just like, in a way, we're expressing radians, the number of radians, theta, as a function of time, right? What we're ultimately saying, Yes. Ooh, nice. Okay, so let me back. There's two things in the direct chat. So one person in the direct chat a couple of minutes ago said, so is K the slope? And like she or he totally like nailed. Yes, totally what I'm saying. And again, I just want to make clear to everybody, the slope of that graph. I don't mean that K is a slope anywhere like in the shape of the oscillators, like not in physical space. It's not like a steepness, but yes, it is totally the slope of that graph. And then someone just wrote down in the direct chat, someone wrote, so Kx is its own little linear function with in the larger function of y, in the larger function of y. Yes, I am ultimately, so yes, that's very good, other direct chat person. I am ultimately saying, what I'm trying to emphasize to everybody, even though I know we've like sort of already done this, but I'm trying to expand now. I'm saying to everybody, this is a big deal because this function is the first time we're seeing in science. It really is the first time that we're explicitly seeing in a science class or any math class that any of us has been in so far. This is the first time that we're seeing a function of two variables at the same time. It is a big deal. We have two, well, okay, so first of all, y is the dependent variable. Y is the dependent variable. It's the output of this function. So specifically what we mean in physics, or in this case, we mean y, what the function is spitting out is how high any individual piece of mass, any particle, any individual piece of mass, anything on the edge of any oscillator, how high it is in how high it is, what its vertical position is. That's what y is. That's the output. It's like someone's walking into, so we've got all of these masses going up and down on springs all at the same time, but this is very, right? Like all of these masses going up and down on springs at the same time, and they're all doing it the same way, in the same rhythm, all that. It's just they all have different head starts. They all have different head starts, just that all of their different head starts themselves are a pattern, right? So each one of these things is moving in a pattern in time, but they're distributed throughout with head starts that constitute a pattern in space, right? This is a function of functions, like someone's saying in the direct chat. Oh, and someone, and a couple of people a lot of things are happening. The lights are going crazy. All right, I'm going to look in the direct chat. Let me just finish this one sentence for my early onset of death. I guess that's, yeah, early onset Alzheimer's. But I guess I've had that since I was born. And what would early onset of death be called? Life? I don't know. Anyway, what I want to just say, and then I think cool things are happening in the chat, is is that you have all of these oscillators that are all going up and down, up and down, up and down, each in their own individual pattern. But they're all going up and down in a pattern of patterns, right? What this is really like right? So what this is really like, if you've ever, I mean, before COVID, if you happen to ever be in the greatest borough of all, I mean, one particular borough is called Brooklyn. Not saying I'm biased toward Brooklyn or anything, except I totally am. But if you've ever been to Brooklyn, if you've ever been to the Brooklyn Museum of Art, like on Eastern Parkway, some of you have, some of you haven't, but there's a fountain outside the Brooklyn Museum of Art on Eastern Parkway. That at least before COVID, it was this big fountain, and it literally did this. Like it had all these, and I'm sure there's other fountains like this other place. I mean, I'm sure Queens has one. I just don't know where. It's not at the Museum of Science because it's not at the Hall of Science because I love that place too. But whatever. There's like all these fountains, and like, so water goes up and then down in the first one, and it goes up and then down in the second one, and then up and then down in the second one. And if you look at it, it's pretty fascinating because you can see that each one of the individual things is doing a pattern in time, but then you stand back and look and you see a very clear pattern in space. And if at any moment you took a snapshot in your mind about where the tops of the waters are, which is just what I'm talking about, you would see like a cosine graph being formed by where all the tops of the waters are at any given moment of time, if you can relate to what I'm talking about at all. But if you just do it with springs, and in fact, there's like a big contraption at the back of the lab, your lab, our lab. I guess it's made with pendulums, but another similar thing where like everything at every moment is at a different height. But then the next moment, all the heights change. But oh my God, there's two 8-year-olds upstairs who are
about to, like, as though I'm not distractible enough, literally the ceiling is about to fall down. Okay. I'm going to look in the chat in a second. But yes, everything I've seen in the chat so far is correct and insightful. What I'm trying to say right now, the one thought I want to finish before I look in the chat is that what we now have is that the dependent variable is height. The output is height. It depends on two independent variables. And that's actually a big deal. It's actually a big deal. There's two independent variables. When we say two independent variables, horizontal position measured in meters, and time measured in seconds. When I say there's two independent variables, I really mean it. I mean x and t are each independent, as in they are each the input for this function. But I also mean, and this is what you were trying to see in lab 3, it's not just that x and t are each an input for this function, but they are each independent of each other. And that's really what we mean by an independent variable. X is driving y, while at the same time, but without any interaction or interference from x, t is also x is driving y, is what I meant to say. And at the same time, but without any interference or interaction from x, t is also driving y. They are independently of each other, contributing to the ultimate output called height. Last thing, and I'm going to look in the chat, I'm saying that what this function means is, if at any moment, if you just walked in and you saw all of these oscillators going like that, and you said, hey, how high is the mass? Which is what you're asking the question, like, what's y? I would say to you, well, wait, in order to answer the question, how high is the mass? I need to know two things. I need to know when you're asking, like, how high is the mass now, or how high is the mass now, or how high is the mass now, right? I would need to know the time in order to tell you how high is the mass, but also I would need to know, where are you looking? Which mass do you mean? I mean, there's mass over here, there's mass over here, there's mass over here. So in order to find out how high a piece of mass is, you have to specify a certain point in time and a certain point in horizontal space. Once you've specified both of those things, once you've specified the moment you're looking, and this is all what lab 3 was trying to do in like a different way. Once you specify the moment you're looking, and you specify how far out on the x-axis you're looking, then boom, we know. What, or let me say in the other order, once you say how far out on the x-axis you're looking, then we're like, oh, if he's looking over here, we'll multiply an x of 17 meters by the k of 35 radians per meter, right? Like k could be is any number of radians per meter. So we're like, oh, as soon as you specify x, we multiply x by the number of extra radian head start that we get for each extra meter. So we multiply x by k. That gives us our phi for that mass that we're looking at. And then we're like, oh, he's looking at the third second. So we multiply the time by the radians per time, the angular frequency, the rate at which this thing is going up and down in time. So what I'm trying to say, and this is it, and I look in the chat, I'm trying to ultimately say, if nothing else, I'm trying to say, this is like a Miller's analogy from SATs or whatever. I'm trying to say omega is to time as k is to space. Literally, angular frequency is to time as angular wave number is to space, literally saying omega tells you how many cycles an individual oscillator does per time, and k tells you how many cycles can fit along the x-axis per space. Radians per second, radians per meter. That you put those two pieces of information together, horizontal space and time, and now you have this collection of phase-staggered oscillators, which in the end of the day, what we're saying is, and I know you know this, but I'm saying it at the end of the day, this is wave motion. This is, so you make a wave out of a collection of deliberately organized oscillators. A wave A wave is a pattern of patterns. In fact, I'm going to say one more thing. I know I keep stalling on the chat. I'm sorry. The one last thing I'm trying to say that I'll say a lot for the rest of the course and that you were trying to say in lab 3, what we're really saying is if you really want to understand what a wave is, and a wave is not a thing, right? A wave is a type of motion. A wave is unthingy. And I'll say why that is again 100,000 times if anybody ever asks me, or whether they do or not. A wave is not a thing. It's a type of motion. A wave goes from left to right. No individual thing goes from left to right. Right? A bunch of masses go up and down in their individual neighborhoods. Therefore, we see a crest or a trough or a pulse or a disturbance go from left to right. And so it exists, it's measurable, it's analyzable, it's predictable, but it ain't material. The wave that goes from left to right is real, but it's not a thing, it's not particular, it's a pattern of patterns. And what specifically, and this is my last thing, what specifically a wave is co-sinusoidal oscillation. This is what a wave is, right? In order to make a wave, you've got to create co-sinusoidal or harmonic, in other words, harmonic oscillation in time and space at the same time. You're having a bunch of things that are oscillating in time and in space at the same time. That's what constitutes a wave. All waves consist of harmonic oscillators, but no individual harmonic oscillator itself is a wave. That's what I'm trying to say, big picture. Again, all of this is just an extension of problem 4. I'm going to do something much more specific with it now in 2 minutes, but I'm going to look at the direct track first because clearly things are happening that are good in the direct track. Okay, sorry, that's okay. Is its own. So yeah, so this is a function that consists of little linear functions. Yeah, this is a cosine of 2 individual linear functions. Technically, this is a superposition. This is a linear superposition of 2 independent cosine functions. That's another fancy way of saying it, but yes, I agree. It is, yes. Then there's more. So can the linear function? Yeah. And so one person wrote in the chat, okay, I'm going back now like 11 minutes, but somebody wrote, so Kx is its own linear function within the larger function of y. And I'm saying, yes, I totally agree. And then someone wrote after that, so can the linear function be phi equals kx? Yes, exactly. Like that, just to agree. Yes, that's what I'm saying. Yes, phi is a linear function of x. That's awesome. Just like omega, just like theta is a linear function of t. And by theta, I mean like how many radians you are into the cycle. So yes, totally. So now there's more in the chat. So if you want to get us, okay. I'm gonna quick. So this is why I do like this class. See, you put me. I start off in such a bad mood for my own reasons, and then you put me in such a good mood, all of you. Because this question in the direct chat, I'm going to read it quickly, but I promise you that this question that I'm about to look at, there's more, but the one I'm looking at right now is the question that exactly pushes us to the next thing I absolutely want to do. So it helps move us along. Someone is saying here in the direct chat, so if you wanted to get a second order differential equation from this, which I totally do, thank you very much. And it might or might not look exactly like the front page of the notes today. But yes, if you wanted to get a second order, did anybody ever think they'd be in a room of people where someone would say, I want to get a second order differential equation from this? But good, yes, so do I. And yes, if you wanted to get a second order differential equation from this, would you treat Kx as a constant since it is phase shift? Or would you have to differentiate with respect to x in some way? Oh my God. Okay, I don't know if I'm reading it clearly or not, but that question is right on the money. I might read it again in a second. Like basically what the person's asking is hang on. So if we do want to take derivatives, it's like what seems to be like what we do in this class all the time. If we want to take some derivatives and like somehow get a differential equation or something from this, like, do we person's really asking is, are we going to treat X like a variable or like a constant? That's what they're asking. Like, how are we going to take a derivative? Are we going to treat X like a variable or a constant? That is exactly the right question and the fast answer, but this is exactly what we have to get into today. Exactly. And in theory, by the way, this is what you did for your analysis day on lab 3, like the day that you had to come in and do a bunch of analysis, even though you probably resented it and probably thought maybe you should have stayed home and whatever. We had that debate in our minds too. But the day that you had to come into lab and do a bunch of analysis on this is what you did. But now we're going to do it together in a lecture format. And exactly the right question is what she or he is really saying is, how do we take derivatives of functions that kind of seem to have more than one variable going on? Like, have we ever actually done that before? And the answer is no, we actually have never done that before. But yes, we most certainly can, and there is a way, and that's what I'm here to teach you in like 2 minutes. But it's so much better now that at least one person in the room is actually asking that question. So what I'm going to do in 2 minutes is not out of nowhere. It actually is the natural next step, as at least it seems to be in one person's mind. And I'm not going to make too much of a big deal of it. Yes, I am too late. I just want you always to know, it's not that I want to single anybody out either. It's perfectly appropriate that it's in the direct chat. But I just want you to know that all of you, if you were given enough time, and you had no other distractions and you weren't hungry or like have other classes or other big important issues in your life, if you were left on a desert island, the truth is every next math or physics step that we take in this class, you would have come up with it on your own, really. Like, it is all a natural logical progression. It's just the natural logical progression that is developed by people who are thinking about nothing else. So they just move forward on this track. But you see, that's why I'm excited every time one person in the class even says like the next thing before I say it. It just shows there's something that is not out of nowhere about this. The next thing we're going to do is exactly what someone just asked, which is, how the heck do you deal with two independent variables in one function if you want to take derivatives? It is the best borough. Okay, and yes, it is. All right. So now I'm moving on in the chat. I like how that's the one that went public, that it is the best borough. Oh, 2 people. All right. Look, I'm not going to say that I was totally born in Brooklyn and lived there like most of my life. I'm not going to say. And I'm not going to say that I'm not going to say that my younger son was born in Brooklyn. And I'm not going to say that my father was born in Brooklyn. And I'm not going to say that his father was born in Brooklyn, but I'm not going to say it. Good thing I didn't say it. Okay. But it may or may not be true. Okay. Now, I love Queens. Some of my best rival boroughs are Queens. And Staten Island. Yes. Okay. Anyway. All right. So I'm totally kidding, except to the extent that I'm not. Okay. So here's what we're going to do right now. I mean, look, honestly, I am sort of, I am from Brooklyn. I'm biased, but yeah, no, Queens is very cool. All of New York is cool. I mean, yeah, okay, Queens definitely has the best science museum. There's no question about that. Probably at this point, Queens has the best schools too, but okay. Anyway, so here's what we do. Wait, sorry. I that is true what I just wrote, but let me back up for one step to make this clear. Sorry. Okay. I'm going to start by saying something that seems really stupid. Right? What I wrote on the board, this seems stupid. Hopefully it seems stupid to you. It is actually true and it's not a joke. But what I wrote on the board right here. Oh, wait, I'm sorry. There's one more thing in the chat. I'm sorry. Oh, Queen's Patio. Okay. What I wrote here, bear with me for a minute. This is to make a point. I'm saying if you have a function of one variable, the infinitesimal, and you picture it like as a graph. Right? You pick some arbitrary function, some arbitrary graph. The infinitesimal rise in that graph, and I'm zooming in like this is a big magnification, diagram not drawn to scale. The infinitesimal rise in that graph equals the derivative times the infinitesimal run, for the sort of dumb, obvious reason that the derivative is infinitesimal rise per infinitesimal run, right? Like in a way, what I'm saying right now is almost circular. It's almost a stupid thing to say, but I think it's correct, and I think you'd agree with it, right? If derivative means rise per run, then if you ever want to know, hey, how much did that rise? How much did that graph rise over there? Well, one way of, if you knew the derivative of the graph, if you knew the rate of rise per run, you could take that derivative and multiply it by run, and you would get rise, right? Stupid but true. I'm almost, wait, can I, in fact, I'm going to change the view and just look at it. Can I just get an electronic thumbs up? Even if you think that's stupid, even if you think that's stupid, yes. Okay. Thank you, Valentina. Thank you, James. Thank you, Michaela. All right. Also, I love the animations too. That's so new. Okay. Great. Okay. Now, why did I write something so stupid as that? Because we can extrapolate from this. We can generalize from this and say, thus, if, I don't know why I'm changing colors, but thus, if y is a function of more than one variable, if y is a function of, say, x and t, and you want to know if you want to know the infinitesimal rise in y, you could do the same thing. You could do like this, the derivative, the infinitesimal slope times the run. You could do the same thing. But if there's a function of more than one variable, so now this is getting at the direct chat person's question, right? If it's a function of more than one variable, then there's like more than one way the graph can run. Put another way, if it's a function of more than one variable, then really what we can't capture the whole graph in one two-dimensional picture. What lab 3 was all about was really realizing that what you did was you took a movie of a wave pulse, right? You took a movie of a wave pulse, and then you broke down all your data and your analysis. You broke down your data and you split the data into two, you split the phenomenon into two independent functions, right? You made two different graphs in lab 3. You made a y versus t graph for any one given constant fixed x, and you made a y versus x graph for any one given constant value of t. And I'm going to say that again a million times, but that, if you think about it, that's what you did in lab 3. You realized that, I mean, you didn't realize this consciously, but by realizing that we've got pieces of a metal spring that are changing their height depending on both where in the spring you're looking and when in the motion you're looking. What you did was you divided everything up and you created two graphs. One was y versus t, and the other that was independently happening was y versus x. Because you can't, if you were to put all of this into one graph, it would have to be a three-dimensional graph. It would have to be like in a cube of graph paper, right? You would have an x-axis and a t-axis, and then height would be a function of both of those, right? Meaning that if you ever wanted to know how high the graph was in any place in the graph, you'd have to ask yourself, how far over on this axis am I running? And multiply that by the slope. And also, how far over in time am I running? And multiply that by the slope. And both would contribute independently yet simultaneously to the overall answer of how high the spring was at any point in space and time, right? It's just like vectors are the sum of independent yet simultaneous components. This whole situation is a sum of independent yet simultaneous runs along the independent variable axis. So what we would say for the rise of a function like this is we would say that dy must equal not changing, just okay. Now, again, this is getting at, I'm going to show you how to do this, but this is getting at the direct chat person's question. Okay. This is a new piece of notation. Okay. Again, let me make this very clear. I am not referring to something that I think you already know. I'm not using notation that I'm asking you to remember. I'm telling you this is a new piece of notation. I don't expect you to already know this. I don't want you to already know it. I want you to see it happening right now. I'm saying from now on, whenever, I mean, it's a real thing. I'm not making it up. This is it's very real math and physics. But I'm saying from now on, if you see that symbol that looks like a backward 6, I think, yeah, it looks like a backward 6, or it sort of looks like some sort of lowercase Greek or Celtic letter or something, but it actually isn't. That thing is called a partial or partial derivative. When you see partial y over partial x, we read that in physics and math to mean the partial derivative of y with respect to x. Remember, and this is why one of the reasons that I never write my derivatives as like f prime or f double prime or something, or f dot, f double dot. Like some of you have asked me about that in homework, and it's very legitimate and cool that you've asked me. But one of the reasons that I strongly prefer the dy over dx type notation for derivatives is it makes it clear what's the rise and what's the run. What is being changed as a function of what, right? So if you just write dy dx, dy over dx, you mean the derivative of y with respect to x. But if you write it with these weird backward 6s, what you're now talking about is something that's technically from multivariable calculus. You're talking about, but this is all we need to know about it. What you're talking about is partial derivative of y with respect to x, or in the second case, partial derivative of y with respect to t. And what we mean by that, and again, this is all a thing that occurs that we have to be very careful of once we have a function of more than one independent variable, which is what we have here and we've never had before. When we say partial derivative of y with respect to x means Okay, what this means, and I'm going to do it like before you in next. I'm going to do an example for you, and it's not just going to be an example, it's going to be like the whole point of all of this. But again, to answer the great question from direct chat, I'm saying there's a thing called taking a partial derivative. Well, I'm saying there's a thing called taking a partial derivative, which is something we do whenever we have a function of more than one independent variable. When you take a partial derivative with respect to one certain independent variable, what you do is you temporarily treat all the other variables as constant. What we're saying in mathematical terms here is if you want to know the rate at which a three-dimensional function, a function of two independent variables, like a graph in a box rather than a graph on a piece of paper, the graph that you did not make in lab 3 that you split into two graphs. But if you just made one graph where it was y as a function of x and t, if you ever wanted to know how high that y was, you'd have to say, well, if you ever wanted to know how much higher the graph got in a small interval of space, you would say, well, how far over did I walk on this axis? And you'd multiply that by the rate of change with respect to that axis, right? If you had some rule in your mind that for every meter over the x-axis, the graph climbed up 3 meters of vertical space, you would say, aha, well, I walked over 2 meters on this axis, and the rule says 3 times for every meter. So I will multiply 3 times 2, and that's bringing the graph up by 6. But then at the same time, you'd say, but hold on, I also moved over 3 units of time on this t-axis, and there's an independent slope that's independently saying for every unit of time that I move over on this axis, I have to go up 7 units of height or something, right? Like each one has its own rule, its own little individual slope, or its own individual, what we call partial derivative. There's a rate at which the graph changes as a function of that axis, and independently, but simultaneously, there's a rate at which the graph rises as a function of the other axis. What we're saying is, in total, if you want to know how much the graph rises over any interval, you got to take into account both of those contributions and add them together, right? That's what this statement right here is saying. So, and I will look in the chat in a second. Sorry. Okay. So this statement is saying it's got to be the sum, the simultaneous addition of these two independent contributions. One is the rise per one kind of run. The other is the rise per the other kind of run. Each one has to be multiplied by their appropriate kind of run, right? The last thing we're saying is each one of these is truly independent. So each one of these little slopes, these little derivatives, we get by taking the derivative of the function with respect to the particular variable in question, and we temporarily treat the other variable as a constant. That's what it means to take a partial derivative. It means to take one derivative piece at a time. Of course, I'm going to do it in a minute to make this concrete. But I do also want to say that therefore the answer to the question that the person asked in the direct chat, like what we're saying is, yeah, it's going to turn out that we're going to take two different derivatives. One derivative where we treat x as the variable, and in that case, we're going to hold t constant. And the other, we're going to take the derivative of t, and we're going to pretend x is a constant. Basically, the answer to her or his question is, yeah, we're actually going to have to do both, because you're absolutely right to ask. There is an issue here. We have to cover both territories. I'm going to do it. I'm going to make this concrete, hopefully, in a second. But there is two things happening in the chat. Hang on. Oh, right. Oh, exactly. Yes. Okay. So I guess it's two from the same person in direct chat. So you do the derivative, and I'm going to do it, but yes, just because so you do the derivative treating kx as a constant, and then you do it again with wt as a constant, they're saying. And yes, and I'm going to, for anybody who didn't catch that, like I'm totally going to do it, but I'm glad someone did. Yes, the answer is yes. That's awesome. And then you add them, and then you add them together, depending on what you want. You add them together if you want the full ultimate differential, if you want the complete total rise. For our context in physics, to complete this theorem, yes, you add them. We may not literally have to add them depending on what the information we want to get out of this. But right, you got it. So, all right, hold on, pause. So we're going to do it right now. Okay. Okay, so I'm going to do this now. Sorry, there's a lot of distractions. Okay, so I'm going to show you. So now I'm going to do an example of what I'm saying, but it's not just an example. It's the actual physics that we're talking about. It's the whole point. So I don't know why I keep going to do. I keep writing plus or minus because it could be plus or minus, but just to make this clear, but we can pick either example we want. It comes to the same thing. And then also you can totally adjust it depending on how you define K. So, all right, I'm going to call it plus. I'm partly calling it plus or minus because in case you see on the web, sometimes they do minus. It doesn't matter whether you do plus or minus or what. But that's our function, right? And again, this function, I hope it's increasingly clear to you what you were trying to show in question 4. That function, first and foremost, describes this collection of phase-staggered oscillators. But what I'm trying to say over and over again is once you stand back and you look at a collection of phase-staggered oscillators, what you have is wave motion. So this is wave motion. And you might want to stop me at some point in the chat or something. If that leap, I mean, it's not a leap, like that's the connection you were meant to try to expand on and show in problem 4 of the exam, but that doesn't mean I don't know how clear it is to people until I grade your exams, which again, it's going to take a little while, and I apologize for that in advance. Geez Louise, that's not the wave equation. Wave motion is what I mean to say. But I hope it's increasingly clear to you. What you're trying to see as we progress is that equation describes wave motion. But you're going to see that even more if we ask. I'm going to take the partial derivative of y with respect to t. That's what I'm asking. Now I'm going to do it because we've never done this before. But, well, actually, I am. But I'm going to give you a moment to try to take, just to see if you understand what I'm saying. I mean, I think at least one person does. Don't put in the public chat for this one. If you wish, in the direct chat, just take one derivative of that expression, treating t as the variable. But what I'm saying is, if you're going to take partial y with respect to t, if you're going to take partial derivative of y with respect to t, the whole idea is that you're going to treat x as a constant for this question. Then, as someone pointed out in the direct chat, then we're going to do it the other way. We're going to take the other partial and we're going to treat t as a constant. But for this, I'm going to pause for a second and give you a moment. You don't have to, obviously, but in the direct chat, please. Oh, good. Someone's already, all right, good. We'll definitely, I'm going to look at the answer in a second. Someone definitely understands the question in the direct chat, that's for sure. But yeah, definitely keep it in the direct chat for now. I don't want you, okay? And either put in an answer for partial y, partial t, or if you want to honestly say, like, I've lost you, or this is what I don't understand, or say, put something in the direct chat if you wish, not in the public. I'm going to give you a moment to think about this. Okay, I'm going to give you a moment and I'm going to respond in a second also. Okay, I'm looking in the direct chat. Okay, so first of all, everything in the, do I want to respond? All right, I'm going to respond to these direct chats. Also, all this counts, you know, you can submit this for points, whether you're right or wrong, all that stuff. Hold on, I'm going to try to respond to these. Oh, and but as a habit also, I'm sorry. Okay. I'm just responding to direct chat. I know this always slows everything down, but it's sort of a cool thing that we can't do in real classes. Hold on. So I'm just going through the direct chat in order. Again, I know this is never the efficient thing, but I think this is like very valuable for each of you at like one moment. So hold on. Right, right. Yes, good. So I will stop in a second. Well, a lot of you, and again, let me compliment you. So a lot of you really are, I mean, see, this whole direct chat thing, you guys are like, even those of you where I'm saying it's not quite right or it's missing this piece, like I feel like I know what's going on in your mind right now much better than I could any other way. And I feel like this is super productive, even if it's a case by case basis. So bear with me. Boom. Yeah. And really, and each one of you, you got to submit these for points for participation because I can't emphasize enough. All of you that are putting things in the direct chat, like no matter what you're putting in, you've got to understand how much better this makes it for my ability to teach to you. Because now I know where you all are. I mean, you're going to get much more out of class for the fact that you're doing this right now, all of you. And if it helps that it's private, great, fine, all the better. Hold on, I'm still looking. So there's a lot in here, so bear with me. Okay, almost. Almost there. Oh. Okay, almost. Oh, and there's chaos. Cool, cool, cool. I think that's okay. Okay, I think there's one more. Okay, I think, oh, wait, oh. Whoa. Oh, oh, okay. I think- Yes. Oh, okay. Wow. Okay. See, I keep wanting to stop, but I don't because I feel like this is, I know this is like so awkward and weird, especially when you watch the video, but this is so much more productive, really, I think, than like, anyway, whatever. I'm just amazed at what I'm seeing in the, all of you who are putting in anything in the direct chat, you definitely should find as many portals as you can to submit these to, or if you think of a new portal that one of these you can make up for one of these, let me know, like submit. I'm going to make a portal for making new portals. Oh my God, that's like an awesome. Oh my God, Tom Nook total. They actually do have that. Tom Nook. He has like a like, doesn't he have a thing of like getting new Nook miles for submitting for new Nook miles or something like that? But anyway, whatever. The point is, you guys are rocking my world with what you're putting in the direct chat. Like I keep wanting to like get back to class, but this is so much more class than anything I can say. I cannot emphasize enough that what you guys seem to have the confidence to tell me privately is like fascinating. It's like, even when it's wrong, it's like so helpful and specific and clear that you're being a good student too. But when it's like, right, I mean, some of you are having insights in the direct chat that are like, would save me buckets of time, or will save me buckets of time. So again, I'm almost done. But as long as these things keep happening, I'm not going to go back to the board for a minute. But all of you are, as many points as you can squeeze out of this interaction, please do, because you deserve them. All right. And, but I'm almost, I think I'm almost done. We'll see. We'll see. Hold on. Wait, still. Okay. Oh, go back to the previous slide while you, oh, yeah, sorry, sure, absolutely. Also, why is this thing? Yes, I just saw that I'm going out of order. Tell me which slide. You mean that? If someone's asking me direct chat for, I don't know why that. Sorry. Tell me if that's the slide you need, or if it's a different slide. That's the one. Okay, cool, cool, cool. All right, and I think that might also mean that I'm almost done with these. At this point, what I am going to say is I'm going to make sure that anybody that said anything has gotten at least one response. And then anybody who puts in, if I've already responded once, I'm going to read everything, even if you've said more than one, and you could totally still submit all this for points, but I may stop responding like I might in a minute stop responding to multiple things because I want to. Okay. I think I've got. Okay, what am I missing? Just something I'm missing. Okay, I think. Oh. Oh, okay, there's one that I missed. I'm sorry, almost there. Okay. Okay, I think. Oh, did I get? I think that's. Okay. Uh, okay. Okay. This is great. So, okay, what I'm going to do now, it's 6 o'clock. I'm going to stop. If I missed you, I totally apologize. And we'll go back a slide. Yeah, I can go back a slide. Sure. Okay. And now, of course, I'm going to post all this, the PDF and everything of the notes. But yeah, I can go back. what I'm going to do in a minute after you've copied whatever notes you're trying to from these 2 pages. So I'm going to do these out in a second. Now, okay, I'm going to do these out in a second for clarification and to get somewhere in this topic. So bear with me, so hopefully this will make it. So from all that chat, I definitely feel like in a way now I think we all individually progressed forward in the material with that chat, but like, okay, so we're going to do it as a group now. Then please also understand this isn't just an arbitrary exercise. I'm not just teaching. I hope you see the point of this course is we teach the math that we need in order to do the physics. There's no piece of math that we're just doing just for its own sake. And so none of the examples we're doing are just examples. They're like the point, right? So we're going to take we're going to take 4 derivatives of this function. The thing that I just asked you to do in chat, the thing I just asked you that generated all of this discussion, this private discussion, I asked you to take one particular partial derivative. I'm going to do it now for everybody sort of quickly. You can, and if you're still not clear to you, definitely like reach out to me privately, whatever. But then I'm going to take 3 more and I'm going to put them together. Again, I'm going to take a total of 4 derivatives. I mean, we've got 43 more minutes. I'm going to take a total of 4 derivatives. They'll go faster as we go. And by then you'll hopefully see how these derivatives work, but also we're going to put them together to arrive at an important conclusion. And the important conclusion is what someone about an hour ago asked in direct chat, which is like, can we construct somehow a differential equation from all of this, as I think maybe at least one person understands you were doing in lab 3 analysis. That's where this is all heading. That's what we're trying to do. And that's the goal for the next 42 minutes, is to take 4 different derivatives and put them together in one package that will constitute one new differential equation that describes one new physics phenomenon called waves, right? And the point of that is that then we want to use that differential equation to infer and deploy certain constant measurable properties of any given wave. And then you can do homework. You will notice very quickly, the very next 2 homeworks were posted today, and some were taken down, I think, as well. Or say, if there's any homework that you ever see up there that doesn't have a date on it, don't worry about it until it does have a date on it. It's just there, I guess, to give you a sense of what's going on in the course. But there's 2 homeworks now that have been posted that both do have dates on them, I believe. One homework is due this Wednesday. The next homework, the homework 4, is due this Wednesday. Whatever weirdness we're doing with class arrangement in the next 2 days, that homework is Wednesday. I think you will have had some practice and some insight as to how to do it, or you may already have had from one of your labs. That's due Wednesday, not tomorrow. It's due Wednesday. So you have 2 days to do it. And then the next homework is in theory due Monday, but you'll notice when you look at the homework 5 that's due Monday, that homework is all, you could argue it's extra credit. I mean, all of this is extra credit in a way, but that homework is purely to get a bunch of points. It's worth a lot of points because you'll get a lot of points if you do it. But I'm telling you right now, the one that's due Monday, we might not ever explicitly go over. And it's not, I'll tell you right now, the homework 5 that's due Monday is purely for points for you and for knowledge and material accumulation. It's not on the final. Again, the homework that's due Monday, homework 5, you're not responsible for it other than for that homework. And so it's also a warning that there may be another additional homework due Monday. If there is, it would be that one would be of a higher priority. Like the one that's, I'll explain all that again later, but whatever is posted right now for Monday is in effect optional for points. If you don't do it, I'll never be the wiser, and I certainly won't punish you. Okay, but now what we're going to, I hope that's clear. But the homework that is very next, homework 4, is due Wednesday. So there's nothing actually due tomorrow other than, your typical 5-point game turn thing that's due at midnight tonight. Okay, so here we go. I asked for partial y, partial t. Okay, so I'm just going to rewrite this. So we have the given is y equals a cosine omega t plus kx. Then dy dt equal to cut to the chase. Okay, or partial y partial t is, as we said in the chat, it's I'm going to treat t as a variable. I'm going to treat x as a constant. So that whole kx term for this kind of derivative, I'm treating it's as though it says k b or k phi, or the whole thing is just phi. It's just a constant. It's a number. All of kx I'm treating as a number. So only omega is the variable. So I do the chain rule. I decide that the derivative of the whole outside thing is negative a sine of everything in the parentheses. But then I have to multiply that by the derivative of whatever is on the inside. And the derivative of what's on the inside, I guess should I do this into, well, maybe I should write out too, but the derivative of what's on the inside is omega, right? It's omega plus 0 in effect, because k times x, truthfully, x is a variable. But if we're taking the partial derivative with respect to t, that means treat x, hold x as though it were a constant, right? Is what that means. So if I were to take another, so that's the question I was asking. Okay. In the chat, so that's the answer that I was looking for in the chat ultimately. And you should really stop me now if it doesn't make sense, I guess.
Okay, just to clarify, because we're finding the derivative in terms of t, we only differentiate t and then leave everything else as a constant.
Yes, exactly. And wait, let me back up for a second. So the person in the direct chat who said it made sense, thank you for saying that. That's good. But yes, Christopher, who's talking right now, like that's exactly what I'm saying. Yes. And then the way I just wrote it out on the page in symbols is just a symbolic way of saying what Christopher just said. Like if you're doing chain rule, the derivative, if you're treating the inside of the parentheses as its own function, like z of t, then I'm just repeating what Christopher just said and affirming it. Yes, if you're just taking the derivative with respect to t, then you only treat t as a variable, and you like pretend, basically, you treat x as though it were constant temporarily in this context. So yes, I mean, what Christopher said, yes. What direct chat person said, yes. And I'm just finding one other direct chat thing right there, but good, right. Hold on. Okay, so that's that right now. To go to the other side, like what some people did in the chat was they answered, some people in the chat ultimately correctly answered a question that I hadn't yet asked. Some people gave a correct answer, but actually to a slightly different question. So let me make sure this is totally clear. But it is a very important question. It just happens not to have been one I had asked yet. Like, this is partial y with respect to t. I could also ask, what about partial derivative with respect to x? Like, I'm not saying one of these is like more important than the other, not at all. I'm just saying we now split our minds and we treat each one individually. Again, this really is what you did in lab 3. Of course, you couldn't know that at the time, but lab 3 is the experimental physical version of doing this math. I'm going to expand on that in a few minutes, but if we go to partial y, partial x, and again, reminding you that we have this. Then partial y with respect to x is we do the same thing, but now we treat x as the variable and we treat t as though it's a constant, right? So now t is a constant, we're pretending. Therefore, omega t is a constant. So the derivative of that is just 0. So now when we do this one, we would say partial y partial x equals negative a, well, sorry, negative a sine of whatever's on the inside, but then plus chain rule will bring out only a k now, right? So this is an answer now too. Notice this also just very quickly in the direct chat, like some people were like, what I want you to be in the habit, all of you, there's not a criticism, it's an encouragement, again, to move from good to excellent with this stuff. You want to be in the habit, and this is partly the point of the 5-step method, blah, blah, blah. Like when you're asked a physics or a math question, you want your answer to be a complete thought, right? And okay, like in English, if this were a court of law or whatever, if I say like, where did you go yesterday? Like really, if you're being proper or you really want to be as articulate and clear and correct and impressive and everything as possible, if I say, where did you go yesterday? You don't go store, right? I mean, you could, but especially if you were like in a court of law or your life depended on it, or you were like competing for the Nobel Prize or something, and someone said, where did you go yesterday? Or if you knew you were being recorded and your answer was going to be publicized and like mean something later on and be in all the newspapers or whatever, if someone said, where were you on the night of July 17th? You wouldn't say store. You would say, on July 17th, I was at the store, right? Like, and partly the reason you do that, not just because, not just because you're trying to impress people, but you would do that because you're being safe. That way, even if someone takes your answer completely out of context, even if they just print, like you're running for office and they're printing what you're saying in the newspaper and they quote you, like what you said was on July 17th, I was at the store. That's a complete thought, right? That as long as it's true, as long as you're being honest, you'll stand by that to your dying days. Like no one, you're cool with that. I said on July 17th, I went to the store. You didn't just say store, right? It's a stupid example, but so similarly, like in math or physics, you always want everything you're saying to be a complete self-sufficient thought that we can then analyze and trade back and forth and do stuff with. So long way of saying, like really, it's a really important habit, even in the chat or on exams. Like if I'm saying, what's the partial derivative of this function? What you want to say is, partial y partial x equals blah, blah, blah. Like, because you really, right? You don't just want to say blah, 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 because blah, blah, blah by itself doesn't mean anything. It's a complete thought once it has a noun and a verb, and the verb is equals, like no joke. So right here, just notice what I'm really trying to say is what's on the right side of what I did up here, what's on that right side is very similar to, but different from what's on the right side here. Those are two different things. Each one of them is correct as long as there's a left side. What the left, right? This thing that's boxed right up here is saying the derivative with the partial derivative with respect to time is negative a omega sine of blah, 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 blah. And the other thing is saying the partial derivative with respect to space is negative a k blah, 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 blah. Now, this is in fact what you were doing in lab 3. If you really think about I'm going to do more with this. I'm going to take 2 more derivatives. We've taken 2 now. I'm going to take 2 more. But let me just pause again and say, oh, wait. Well, that's a very, wow. Sorry, indirect chat, someone's asking. Wow. Hold on. Okay, wait. Okay, we're going to take two more derivatives, like said, and there are some great insights happening in the direct chat as usual. But I want to make clear this partial derivative thing, like it can seem like a lie, like we're treating each time we take a partial derivative, we're treating at least one variable as though it were a constant, even though it's not. That might seem like a falsehood or like the BS or like a lie to you, but let me just be clear that this is literally what you were doing in lab 3. You had this whole phenomenon, right? You were making waves, wave pulses move back and forth on a long string, right? You're shaking the string and the wave pulses were going back and forth. So you have this whole phenomenon where the height of the wave, the height of the elastic medium was a simultaneous yet independent function of horizontal space and time, right? So then what you did, if you really think about it, you made this whole movie and then you like loaded it into Logger Pro or whatever. Then you, once you loaded the whole movie into the computer, it blows my mind every time I think about this. Then what you did, whether you consciously knew why or not, what you did was you first picked a particular horizontal position, X, right? And you picked a certain horizontal space and you made red dots up and down, up, you made that setting. You checked that box in Logger Pro that said, allow multiple data points in one frame or something like that, right? You check that box where you could put more than one red dot in one frame of your movie, right? And so you made a bunch of stop me if I'm crazy, but and you made a bunch of red dots going up and down, one vertical line. And from that, you generated a Y versus T graph. So what you were doing first is you chose a particular X value. You held X constant. You looked at just one horizontal point in space and you watched how vertical position varied in time, right? You got a bunch of red dots and then you slapped them on a graph and you got this cosine graph. So you got that Y was a cosinusoidal harmonic function of time. Then independently in your brain, like not in a way that was not at all affected by that, but you looked at something else that was actually occurring at the same time as that. What you do? You backed up and you picked one frame from your movie. And again, please, in the direct chat, tell me if like you didn't do this or if you have no idea what I'm talking about. But I think this is what you did. You backed up, you picked one frame from your movie, and then you just looked at the shot, the picture of that frame, and you saw this metal medium, the metal spring stretched out in space like this, and then you unchecked that box, that setting in Logger Pro that says allow multiple points per frame. Or you check that box this time, whatever, you know what I'm saying. And now you made a red dot, a bunch of red dots that captured how high the spring was for any given horizontal position, right? So you were looking at, as my eye traces along the x-axis of this one frame, how high is the metal? And so you put a bunch of red dots there, and then again, you saw a cosinusoidal harmonic function. You saw Y varying cosinusoidally with respect to X this time. How did you do this? Because you only picked one frame. What does it mean to pick one frame? It means to hold the value of time constant. Hold the value of time constant. Treat time as a constant while you analyze the rate at which Y changes with respect to X. So what I'm loudly saying is, we're not lying. We know this entire phenomenon that we're tracking, called a wave, this entire phenomenon that we're tracking, we know X is varying and T is varying the whole time, and together their variation is generating Y. But in order to analyze it, we're saying, hold on for a moment, can we, in this side of our brain, can we just like pick one value of t and see how x affects y? And then over here in this side of our brain, can we just pick one value of x and see how changes in t affect y? That's what it means to take a partial derivative. We're not asserting that x is a constant. We're not asserting that t is a constant. We're asking, how does t change for a given x value, and how does changes in t affect changes in y for a given x value? And simultaneously, yet independently, how do changes in x generate changes in y for a given chosen value of t? When we take these partial derivatives, we're doing exactly the mathematical version of what you do in an experiment, which is to hold certain things constant so that you can see how certain variables affect other variables. That is literally the scientific method, is doing that. It's the whole idea of the scientific method, is hold everything in place so you can see when you tweak one knob, what does Mother Nature do in response to that one knob? We're never saying that Mother Nature only looks at one knob, and we're never saying only one knob ever changes in nature. We're saying the whole idea of science is hold all these knobs still, hold all this still for a moment, and just tweak that and watch what happens, right? That is the breakthrough of science, is the recognition that we can do that. And so here's the math of that science. Okay, now where am I going with this besides yelling at the top of my lungs? I want to take two more derivatives. We've now taken a derivative, a partial derivative with respect to time. We've taken a partial derivative with respect to space. Now let's do it again. Let's do it again. Why? Because I want to take second derivatives. Why? Because I'm a physicist. I always care about second derivatives. Why second derivatives? Because F equals ma. Like really. Because F equals ma. A is the second derivative of position with respect to time. F equals ma means nature seems to happen. Like a interaction occurs at the derivative number 2 level. So I'm going to take another derivative of each one of these. So I'm going to go back to time. Okay. So here's my function again, right? I'm just reminding me the function is this. Okay. So dy, sorry, these are partial derivatives, right? These are all partial derivatives. So dy dt equals negative a omega sine of omega t plus k x, right? That's the first derivative. We already did that. I'm just rewriting it. So now the second derivative, the second partial derivative with respect to time. So I'm going to do it again. I'm going to take derivative again, still only treating t as the variable. So k and x are still constants. So I'm going to do the same thing again. This time I get a cosine, right? It's the same deal as earlier in the course. But omega comes out again. So now it's omega squared, right? So it's very similar. This should be a little bit of a deja vu, right? It's very similar to what used to happen with the single valued functions. But so now we have the partial y, the second partial derivative with respect to y. Oh, sorry. The second partial derivative of y with respect to t is equal to negative a omega squared cosine of omega t plus kx, right? That's the second time derivative. Let's do the space now. So again, the function was y equals a cosine omega t plus k x. So the first derivative with respect to space was negative a k sine of omega t plus k x. But now we want the second derivative, so we're going to take, we're just going to take the derivative of the first derivative, just like we always do. So it's negative a k cosine omega t plus kx. Hello. Oh my gosh, that's bad. 1 second. How bad is it? so bad. Okay, it's not that bad. So right, but if we're taking the second derivative, so chain rule, the k comes out again. The omega does not. The omega and the t are treated as a constant here, but the k comes out. So it's negative a k squared cosine omega t plus k. Okay, now we've got 18 minutes left. Oh, sorry, hold on. I'm looking at the chat. Look. Right, exactly. Hold on. Hold on. Hello. Hi. So yes to direct chat person. I'm writing. I'm going to read this in a second. Hold on. Okay, so someone wrote in the direct chat, so respect to t, it means respect to time, but with respect to x means with respect to position. Yes, totally. That's exactly what I'm saying. Yes. So, so we have this now. Now, we've now taken 4 derivatives, 2 derivatives with respect to time and 2 derivatives with respect to horizontal space, horizontal position. And again, remember, those are the 2 inputs, time and horizontal position. The output is vertical position, right? This is something happening in space as a function of space and time. So we've taken 4 derivatives, but so what? Like, what do we do with these 4 derivatives? Well, notice. Well, I'll just remind. So here's the second derivative with respect to space. And just as a reminder, here's the second derivative with respect to time is, I mean, I'm just.
I have a random thought. Are you gonna try to see what's coming in a sense where you know that at this point negative cosine wt plus kx, so you're basically gonna make both equate to that?
Right. I absolutely. I want to relate the time derivative to the space derivative. I want to relate them to each other. Yes. And there's 2 reasons. Yes. And that's exactly what I'm going to do. And part of the way I'm going to do it is by noticing that each one, both of these derivatives seem very similar to each other. They both seem to utterly depend on this cosine expression, and it's the identical cosine expression to each. So yes, also agreed. I don't know why I keep changing colors. So let me change colors again. Let's relate the time derivative to the space derivative. Oh, sorry. Hold on. And I will look in the chat in a second. Relate the time derivative to the space derivative. Okay, so what we're going to do is we're going to rewrite each one in terms of that cosine thing. And I'm watching the time. We've got 14 minutes. We definitely will do this. Well, there's one. So we're gonna rewrite each in terms of cosine and then set the cosines equal to each other. And I think that's what Christopher's saying. But that is what we're going to do. So there's one thing in the chat. Hold on. There's something in the chat that's interesting. So here we go. But notice again, so, okay, I'm just rewriting again so we can see what we're doing. I'm changing colors again. So notice we have this, and we're all about the second derivatives now. We honestly, I don't know if it's, we took the first derivatives just for the sake of getting the second derivatives. I don't, largely for the moment, I don't care about the first derivatives, although there's some good questions about the first derivatives in the chat. But my main point right now is all about the second derivatives. So we have this, right? I mean, we just wrote this down. All I did was I took the second time derivative, right? It looks complicated, but all I did was try to isolate the cosine expression by dividing both sides by negative a omega squared. That's all I've done. I'm dividing both sides by negative a omega squared so that I can get the cosine expression by itself. Why would I do that? Because the cosine expression is what's in common to both expressions. If I now go to I don't know why I keep changing colors and I keep commenting on it and I just keep doing it. But if I now go to the space derivative, right, where we add this, if I do the same thing, right, exactly. Hold on. So now if I'm going to do the exact same thing and divide both sides by negative a k squared so that I can isolate the cosine expression again.
Question: why couldn't we keep the negative?
No, we could, or you could. You totally could. It's going to go away in a minute anyway. You totally could. There's other ways you could do this, and you could keep the a too, for that matter. You could. To me, this is just the clearest way for me to see it. But yeah, you totally could do that. And if you, and if this were an exam and you did that, it'd be fine. I mean, it'd be more than fine. Yeah.
All right.
Cool. Okay, so but for everybody else, for everybody, yeah, I mean, I'm about to do a thing that's going to show that Christopher's right, that like there's all different styles for doing this, but my point is now I just isolated the cosine and the cosine just because it looked simple. I now have, for everybody who's still with us, we have two different ways of saying cosine. We have cosine equals over negative. We have cosine equals the time derivative over negative a omega squared, and we have cosine equals the space derivative over negative a k squared. So equals have to equal each other. I mean, therefore, so in other words, set equals equal to each other. Set equals equal to each other. But yes, again, this is one of 1,000 ways to do this. There are I should say to everybody, when it comes to any of this kind of algebra, there's always like 1,000 correct ways to do something, and any way you do it that's correct is cool. But word to the wise, I learned the hard way. If there's 1,000 correct ways to do something, that means there's 100,000 incorrect ways to do it. So as long as you see a correct way, that's cool. But if you don't know what you're doing at first, the best thing to do is just like do it my way until you see the point. Then when you see other ways, that's great. But don't just assume that because there's 1,000 correct ways to do something that you'll just figure it out like when the exam comes, because, okay, you get my point. So anyway, I'm setting the two cosines equal to each other. Therefore, I'm saying, I'm going to change colors again. I'm going to say, okay, then this, then this business equals this business, right? And this is where we see, right, like that you might have done it like Christopher's way or someone else, because now we see, oh, okay, that like we see, oh, both of these terms mean, this is like a fraction on top of a fraction. That's sort of annoying, but we'll simplify. We're going to first of all say both of these fractions are divided by -1, so they cancel out. Both of these fractions are divided by a. Like I could multiply both sides by a, and and it'll cancel out. So the a's cancel out. So now what I have is the time derivative over omega squared. Well, what time? Yeah. So now what I have is, and even this result, there's a different ways you could write it, but this I'm going to sort of.
Sorry, can you just go back for a quick second? Sorry.
Yeah, sure.
All right, you can go back. Thanks.
Oh, no problem. Good. Okay. So I'm going to tell everybody now. Okay. Since this is actually very important, we have 7 minutes. So I'm going to say right now, do whatever you want on your piece of paper. I'm going to I'm going to write it. All right. Because this you don't want to mess up, and this conclusion is really important. So
I mean, you're probably gonna say keep, change, flip, but there's like a quicker where you just can you use both denominator. Well, I wouldn't call them both denominators.
What? Oh, wait, what do you? Sorry, what do you say?
Okay, okay, never mind.
Okay, so what I'm going to do right now, and again, I'm not being. There's 1,000 ways anybody could do this, but if my goal is to figure out how the time derivative, the second time derivative, is related to the second space derivative, and honestly, like people, ladies and gentlemen of the jury, that is my goal. I want to see how the time derivative is related to the space derivative and the second derivatives. And specifically, before I turn the page, to be even clearer, even though there's 1,000 ways you could do this, I mean, there aren't really 1,000, but there's like 4 ways you could do this. My goal really is to isolate the second time derivative. I want to get it by itself on the left side, and I will show you why when we're done. My preference is to get the time derivative by itself on the left-hand side equal to some expression of the second space derivative. And you will see why when I'm done. And we will have 5 minutes to reflect, 4 minutes to reflect on this. But so what I'm going to do right now is multiply. I mean, this all looks very complicated, but each derivative is its own little package. So we've got a derivative divided by omega squared equals a different derivative divided by k squared. That's what we have right now. So I'm going to multiply both sides by omega squared, just so I can get that time derivative by itself, that second time derivative, that second partial time derivative by itself. And so what I'm going to get, in fact, I'm going to write it. Well, yeah, what I'm going to get is this. Okay, this is what I'm getting. Or you could even say, I mean, even this, you could write a bunch of different equivalent ways, but let's focus on one way first. I want the time by itself. You'll see why eventually. You'll see why. But I'll give you 2 options. If you're putting that by itself, whichever of these things is more clear, you can write it either of these 2 ways. There's the same. Just whichever way is clear to you is fine with me. But now look, but this that we get, and this is where we're ending today. This is a very big deal. What we're getting here is our second differential equation of the course, right? We had one before for simple harmonic oscillation. We now have a new differential equation. It's very similar to, but not the same as our other differential equation. This one is a partial differential equation. They're both second order differential equations, but the other one was technically what's called a second order ordinary differential equation. This one is technically a second order partial differential equation because it's dealing with partial derivatives, right? The other one had 1 independent variable, time. This one has 2, time and horizontal space, okay, blah, blah, blah. But hopefully you can see, if you look, and we're going to make a big comparison with whatever time we have left, and definitely starting in the next class, like all the next couple of classes are all about comparing this to the other. So we're not done with this by any means. But what this thing is, this is the one-dimensional wave equation. This is called the wave equation. It's the one-dimensional wave equation because this equation captures entirely the motion of pulses as they propagate back and forth along a one-dimensional medium. Let me be very, very clear about this again. And believe me, I'm watching the clock. We've got 2 minutes left, but this is our conclusion. Okay, everything I say now for the next 2 minutes is like trying to clarify, but this is our conclusion. This thing is the wave equation, and the one-dimensional wave equation. Anything that we regard as a one-dimensional wave must be described by this equation, and any phenomenon in nature that this equation describes is necessarily a one-dimensional wave. Why am I saying one-dimensional? When you picture those pulses, right? Sure, they have height and they have width or whatever, but what's one-dimensional about them is that pulses are traveling back, ripples are flowing back and forth along a line, which is that long metal spring that you stretched out in lab 3, right? This is as opposed to waves on the surface of a pond or something. That would be two-dimensional. Now, the equation for that is darn similar to this. I mean, we just tweak one thing. In fact, it's this in one axis and then a similar thing along another axis. But just to be clear, this is stuff that is rippling up and down along an x-axis in time. This thing is saying, I have 1 minute left. This thing is to be compared all of tomorrow, or however we have class time, or whether it's a video or whatever, what we're going to be comparing this to, this is the last thing I'll say, I'm looking at the time, we have 1 minute. Compare this to dy squared. Like, the reason I wrote the time on the left side is because that's exactly how we write it for the harmonic oscillation equation. That one was this, compare to, right? The left side is exactly the same. I mean, it's the derivative of space variable with respect to time. The right side is a constant squared times, well, in simple harmonic motion, it's the variable itself. In the wave equation, it's a derivative of the variable. It's 645. The one thing I'm going to say right now is you might say, wait, but how come a derivative be a derivative? I mean, don't they just cancel out on both sides? No, the left side is a time derivative. The right side is a space derivative. Anything that satisfies this equation from here on in is a wave. A wave is an unthingy motion. When a wave moves from left to right, something observable, measurable, and predictable moves from left to right, but no individual, material, discrete, identifiable particle of matter moves all the way from left to right. Each particle only oscillates up and down. This is the wave equation. You've been very, very patient. Look out for postings tomorrow morning of how we're going to handle, but you can assume that you're not going to have well, look out for postings in the morning. Okay. I'll pause for any questions. I'll turn off the recording, but thank you guys so much. You're great. Homework is
Bye,
due.
Professor.
Bye. Bye, guys. Thank you.
Have a nice day.
Thank you. Have a great
Nice
day.
day.
Thank you. Have a great day. Thank you. Have a good one too. Thank you. Awesome. Okay. Oh, you're all gone. Okay. Thank you all very much. You have been lovely. I am going to now, what am I going to do? I'm going to, yes, I'm going to, I will, in fact, I will bid you all adieu. The wave equation. It couldn't be cooler. Okay, thank you all, and to all a good night.